a Raspberry Pi camera and a robot arm. Let's put them together with a sprinkle of AI magic to give us a robotic cameraman assistant. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, robotics, IoT and other fun slices of tech. If that sounds like your kind of adventure, hit the subscribe button and join the community. I've been dreaming of using a robot arm a bit more like Tony Stark, Iron Man, for a while, though without Tony Stark's budget, I'm afraid. So can I use some simple libraries and bring life into a robotic cameraman? Well, yes and no. This isn't quite as easy as I thought, like most projects. This is a great little project though to revise my robotic knowledge on kinematic chains. That slips from my fingers from time to time, though in this video I'm sticking with Raspberry Pis rather than Picos. I do still have a long-term ambition to put these kinematic chains onto a Pico 2 or derivative board, so a good primer for that project. If this video sparks your inspiration or helps your projects, consider dropping me a tip using that super thanks button below the video, or alternatively there is a payment link in the description. It helps support the channel and keeps these videos coming. To manage the magic in this video, we're going to have to do 4 things. Firstly, we're going to have to be streaming the video from the camera. Otherwise, I'm not going to be able to record it or use it in any way. I mean, I have done this in the past with, if you remember, Robot Santa, and he sort of did facial recognition and face detection and could follow me around the room. But I didn't have access to the video that he was seeing. So he was useless as a camera to me. It was just an interesting novelty device. But this is different. I need the streamed video out of this so I can record it. Then we need to do face detection. Now we're going to do that in exactly the same way I did for Robot Santa. We're going to use OpenCV. That's fairly straightforward. We're going to move the robot as well. Now I've moved this robot before, though this is a slightly cut down version of the full xArm. I've only got 4 servos on this, but we're going to use a Python library to control those servos, and yeah, that's fine. Then comes the slightly interesting bit of controlling it, of actually working out where the camera is pointing just because you know what the angle of these 4 servos are is quite a lot of maths. And then going backwards from where the angle needs to point, if you want to move the camera around and say, well, actually move the camera by X degrees, well, that gets kind of tricky. So we're going to use a standard robotics approach for that called Kinematics, and we're going to use both forward and inverse kinematics. And I will show how to do that. Now this is really useful because it's revising my skills that I kind of gets rusty from time to time before I try and do this perhaps on an RP2350 or a Pico 2. Now I've put all of the code and experiments that I've done on this over on GitHub in this repo, so you can find everything I'm going to point to and talk about. So streaming, yes, we need to be able to see me. I'm not entirely sure why, but I think it's important. So let's put a streaming server on our Raspberry Pi. And the one I'm going to use is a product called MediaMTX. And it's from Blue Environ, and this is great. This evolved from a simple RTSP server that I used to use in the past, but this version is nice and it has some additional formats which we can stream. So setting this up is fairly easy. You can download the binary release, which is what I did, and then we need a configuration file. So let's talk about that. Getting MediaMTX running is actually quite simple. We do need to modify the configuration file MediaMTX YAML or YML. And the reason we need to modify that is we need to actually create the video, the source that we're actually going to publish. And that's actually under the path section. And all I'm going to do is create a new camera called cam. and its source is going to be this special name called the RPI camera, and that's enough to tell Media MTX to pick up the default camera connected onto my Raspberry Pi 3. So after starting up the server, I can actually point straight at this URL and see directly a stream coming from the camera, however disturbing that may be. So for this project, I'm just going to do face detection, understanding this is a human and that they have a face and it's in this location in the frame, not who they are. That's recognition, and that's beyond what we're doing here. So for face detect, I'm going to use the OpenCV library, and I'm going to use that from Python, so I'm going to install that via the pip function. So with OpenCV installed as a Python package and available to us, we can test it out with a test detect script. And what I'm going to do here is basically load up OpenCV and give it a particular trained model for detecting faces. And the model I'm going to give it is this Cascades frontal face. I don't know how to pronounce that. I probably should have researched that, but anyway, it's that model. You can find copies of that online in various places, available as a trained model, nice and easy to share and use. And it's that this XML file that it's basically going to pull in, which is the definition for this trained model, which is I'm not going to explain to you because I don't actually understand it. I can just use it. So what we're going to do is we are going to set up CV2, our OpenCV library, and we're going to give it a capture source, which is going to be a URL, not a local video. In fact, I'm going to run this on my Mac so I can actually see the output and record the output for you. But actually that's the URL, same URL that we use to display the video. Well, actually it's not. I switched actually, because I switched this to using RTSP. So actually slightly different URL to what we used earlier to get the video out. This is also provided by our media server, so that we can actually have a slightly different format, RTSP, in order that we can capture that straight into OpenCV2. And then we're going to basically do a loop here, and we're going to keep reading a frame from our video source. If everything falls apart, then we'll break and give up. And then we're going to run a boundary detect on that to actually detect where the faces are, and let's draw green boxes around those faces and show that on the screen with this im show command. That's it really. That's all that we're actually doing in this code. So how are we actually calling that face detect and what comes back from that? Well, actually that's this function up here that we've written. And the first thing we do with facial detection is we drop it back to a grey image. So we don't need all of the extra data that's provided by color, so we're going to first of all grayscale it. So we're going to get this face detect to run therefore as an algorithm on our grayscaled image. We're going to give it a scale factor so it can scale things down a little bit of 1.1. I'm then going to look for minimum neighbors, and I've set that to 9. This is just trying to clean up where we're getting overlap of images and it's not over detecting. So you need to play around with that a little bit of that figure, but I found 9 was good for me. And then the minimum size of an image for a face, and I'm saying that's 50 by 50. Now once that's run, then our object faces will be the X, Y, width and height of each of the faces in that image. So we can then run this loop here where we're going to loop through all of the faces, and for each face we're basically just going to add a rectangle to our image. And that should give us enough to then go back and actually draw that, which is what we've done. So let's see that running, because the standard fairly demo, all I've done is really made this point at an RTSP source and we can see it recognize faces. And here you can see it following me around and drawing that nice green box around my face. Now the image isn't always perfect and I'm getting some disruptions. That's probably because I think my Raspberry Pi 3A might be a little low spec for what I'm trying to do. So let's turn our attention to our robot arm. Now I've done stuff with this robot arm before, so not a great deal of movement forward from that, though things have changed and the library that we're going to use to do it is actually the same library, it's just changed its name and evolved a little bit. So we're going to use this HiWonder xArm 1S library, and we can install this with pip nice and easily. So this xArm I'm going to use is actually a part kit. I actually bought a part kit off of eBay with a xArm 1S that only actually had 4 servos on it, which is actually technically fine for what I'm going to do to drive this as a camera. So we've got a Z servo right in the base here that's able to rotate the entire unit around via a really nice bearing. And then we've got 3 servos above that. They're servo 5, 4 and servo 3. And those are all controlling the y-axis rotation of the camera. So between the 2 of them we are able to pan and tilt the camera. So to move the arm around we're going to use a library called xArm. And xArm's really nice little library, but it's really moving things at the servo level, which is okay, and that's what we're going to do. So this demo is basically just going to show that we can actually move each of those 4 servos. So the first thing I'm going to do here is I'm going to create our xArm object, and then I'm going to just check what the battery voltage is that we're seeing across the servos and print that out. I've written a little function here that is reliant on this servo's global variable, just because the way that xArm takes, or this library takes servo commands, we actually have to know which of the servos it is, and it basically has a structure where you've got an array of 2 positions and a list of those, and they basically give you, the first is the servo number and the second is the degrees to move to. The other piece into this to be a little bit careful of is if you send a floating point number, this library assumes it is degrees. If you send it an integer, it assumes it is the number of ticks for that servo. So those 2 things are very different, so be careful. So I am being very careful and making sure that what we end up here is definitely a floating point number. So what I'm basically going to do is give this function a list of the 4 servo values in degrees, and it will then move to that angle. And then I've basically set up a list of these to basically just go through and test each one of those servos. So we're just going to move each servo in turn by a few degrees. In fact, increasing numbers of degrees, because it looks more obvious what's going on then. And then we got a loop that's doing it. So that's all we're going to do. So as you can see here, the arm is going through those moves. So how do we work out where the camera is actually pointing based on those 4 values? Well, actually doing it even in my head is really hard, and it makes my head hurt trying to even think about it. But fortunately there are algorithms and mechanisms to do that, and that's what we need to look at next. So this is where we get a little bit robotics heavy with the concept of kinematics. And kinematics is really trying to work out what the angles should be to move a robot, or where the position of the robot will be based on the angles of the servos. So in forward direction, what we do is take those 4 servo angles and we work out exactly where the lens of the camera will be and what direction that lens is pointing in. And reverse is going the other way. So If we know exactly what position we want that camera lens to be and which direction we want it to be pointing in, then can we work out what the 4 angles of the servos need to be. To do that, I'm going to use an excellent library called the Robotics Toolbox, which is brilliant, but there is a slight incompatibility here going on. You see, the Robotics Toolbox is going to use an older version of numpty, whereas OpenCV wants the most recent series of versions of numpty. So for this example, I seem to manage to get away with reversing back numpty to an older version, to version 1.26.4. So I suggest using pip to do a force reinstall to take it back, because that will allow you to work with this Robotics Toolbox, and for the moment seems OpenCV seems to be okay and happy with that. So using this library, we're able to actually model our robot as an algorithm for kinematics. And the way we do that is basically build up, well, what are the transformations going on as you move from the world plane up through each of the different servos that we've got in there. So for servo 6, which is connecting us to the world plane in effect, we've got a Z rotation and we've got a translation in the Z axis up 4 centimeters, or 4.3 centimeters to be exact. Then as we move up to Y, well, we're going to move up a further 3.2 centimeters on the Z axis, and actually just out by 0.2 centimeters on the X axis, before providing a Y rotation as well. Then for servo 4, we're actually going to again go up another 9.7 centimeters and have a Y rotation, this time flipped, so it's the opposite way round to usual, so it's clockwise becomes anti-clockwise, etc. And finally, well, nearly finally actually, we've got servo 3, which is going to go up yet again another 9.9 centimeters, and it's going to have yet another Y rotation. I say nearly there because in actual fact we've still got another 7 centimeters to go to get to the actual lens, so we need to put that in there, otherwise we're not going to calculate the exact value of the lens. So using these descriptions, we can actually build a model of our robot inside Python and get it to start doing that forward and reverse calculations. So here's a model of the robot arm, just as we've explained, that I'm setting up here using the Robotics Toolbox. And so I'm basically describing each of these actuators and how the arm is constructed, and I'm doing that from the position of the world up through the bottom actuator or servo, which is the servo 6 to servo 5, right up to my arm sort of servo 2, which would be a servo but actually is the 7 centimeters that we need to then get to the center of the lens. Then I can create a ETS, which is this chain of transformations, which describes the robot, and that's exactly what we're setting up here. And I can print it, and it can show me each of those transformations as they would happen. Now, using that, I can then say, okay, if we say that each one of those servos or actuators is at 0 angle, because they're all angles, so we got Z and then 3 Ys. If they're all set to 0, then I can actually give that to our chain and ask it what the position of the end actuator is. So where does the camera pointing? And that's what we're absolutely doing here. And the answer that comes back is, of course, a nice massive matrix, of which we have a 3x4, which is basically the rotation transformation matrix, and then the final column we can actually see the X, Y and Z position of the actuator. And if you set them all to 0 with this robot as it's set up as I've got it, then pretty much that's 34 centimeters high, which is the answer it comes up with. Now we can actually go the other way, but the other way is kind of tricky. So what we've done here is what is called forward kinematics. So we've taken the angles of each of the actuators or each of the servos, and we've calculated the end position of the robot chain. Great, fine. Going the other way, the problem is when you've got more than 3 of these actuators, then the number of answers you could come up with is potentially 0 or greater than 1. So, you know, we might come up with there's one position we could get to, we might find there's none. We might find that actually we could do this in 2 positions. So this isn't entirely perfect, but this is the numeric approach to doing it, and that's what we're basically going to do, the inverse kinematics calculation using a numeric approach. And to do that, we're going to set a number of iterations we're going to allow it to go through, and a number of searches we're going to allow it to go through, and we're going to give it a tolerance that it's trying to achieve. So it won't achieve exactly the position we're asking it to get to, but it will get somewhere near it. So I'm actually, in this example, going to ask it to basically try and go backwards from the set of position that we've just come to, and tell me what should the 4 servos be set to get to that position. So I'm giving it our start position, which is basically what we've just evaluated going forward, kinematics. And we're going to ask it, give it those iteration count, the search count, the tolerance we're trying to get to. And here we go, and we can run that. And there are no joint limits I've used as well. We can run that, and I can print out what the number of searches and what the result is. And you'll see that the result that we come back with in terms of transformation is not quite the same thing. So we have all of the 4 servos are close to 0. They are not exactly 0, but they are close to 0, which is okay, I guess. We gave it a tolerance, and that's what we asked it to do. And so if you go forwards from that, it will get too close to the same position we just specified, but not exactly. But this branch of maths is a complex search space, and so that's kind of what we would expect. But anyway, this is how we can calculate where that camera is pointing, and also I can give it a position I want the camera to be in, and it will calculate what I need those angles to be on my robot. So let's put all of that together to create a robot camera. And by all of that, I mean we can stream video from the camera so that I can pick it up and record it wherever I choose. I've got face detection running using OpenCV. I'm moving the robot using that library that we've already seen, and I've got kinematics to do the calculations to actually move the robot around. So let's do a little bit of a test, and we'll see that the robot and the camera is now following my face as I'm moving around in front of it. There are positions where it sometimes gets into unusual angles that I wouldn't have predicted, but it's still always looking in the right direction at the right place, because that's what that kinematic algorithm is doing for us. And of course, if we actually see the image recorded off my screen from a browser session of what the camera is showing, it's nicely following me around the room as I move around. The camera gently is rotating. Occasionally there's a little bit of a jump, but actually this is pretty good as sort of following me around. I wonder, looking at this from a framing point of view, perhaps my head needs to be just a little bit higher in the shot than actually the true center position, which is what I've written the algorithm to do at the moment. But there's an improvement I can make. So I think we know enough now to create a robotic camera, or at least a simple one. There are some other more complex areas we could go into. But we are able to stream our video source. We're able to take frames from that stream and run a facial detection algorithm on it. We're able to move our robot based on just moving the angles of the servos, but also modeling the position of where we want that camera to point and where they want that camera to be in space, doing the full kinematic algorithms. So that allows us to then move to this script, which is going to detect my face and hopefully keep panning towards it. So we're just going to set up a few of the things we've already seen. So our arm to connect, what the servo numbers are. We're going to have an array of the previous radians that the servos were all in, the number of iterations that we're going to allow, the number of searches we're going to allow, the tolerance we're looking for. The speed I want the servos to rotate at, or the maximum speed, which is going to be 1 radian per second. And also the position I want the robot to start in, which is going to be, I want the camera to be at a Y of 1.4 radians, a Z of 0 radians, and I want it in height in meters to be 0.24, so 24 meters high. Now, in actual fact, that's going to be how I'm going to control everything. I'm going to use a Y, a Z, and in radians, and a Z in meters. Why that? Because that kind of makes it simple, because if the camera is constantly just hovering around that center point, pointing at me, that will do, to be honest. So we'll come back to that in a second. So we're then going to set up the definition of our robot, just as we've done previously. So I'm going to set up each of the links and servos. And I'm going to even put in here another start location called a TEP, which is basically just got everything hard-coded in there just in case I need it. I've got a feeling I moved away from using that and didn't refactor it. If that is the case, my apologies. Now, I talked a minute ago about that just controlling things by the angle on Z and Y, and then the height above on Z, that we are above the world point. Now, to do that and to create that then into a matrix that looks like that TEP up here, that's quite a bit of work. And do I really want to do that? Well, is there a simpler way to do that using the techniques I've already told you? Yes, there is, because we could describe a simple robot that actually has basically a joint for Z. It has the offsets for X and Y, and it has a joint for Z in terms of sort of linear motion, and a joint, angular joint for Y. So yeah, that's transformation joint. So that could be our simple robot that we could just use to get me a position of where the camera should be. And it's actually that's that I'm going to use. So I've basically defined a simple version of the arm to give us a camera position. And I'm going to use that to calculate my target position and then calculate what the real 4 servo values should be. So what I'm going to do is I'm going to go forward on our simple arm in this transformation routine, and then backwards from that position in order to work out what the 4 servos values should actually be. So we can go for our using our simple arm definition and give it the radians for Z, the meters for Z, and the radians for Y. That will give us back a position and Euler or rotational axis position for the lens. I can then can that in to my actual robot definition, which is the ETS here, and we can get that to then do a calculation in the inverse direction to give us the angles for RQ, the rotational angles of the 4 servos. And then I can pass that on, provided we succeeded, to actually the servos to actually move. The servo's move function is very similar to what we've done previously. The only differences in here really, or well, there are 2 differences in here. One, I'm making sure that we're actually converting what is in radians into degrees before I pass it on to my function of our arm function to actually calculate. And where they are outside the 180 degrees or positive value, I'm actually just adjusting it so that they're between minus 180 and past 180, so that they're actually zeroed properly. And that's all we have in there, I think. Oh yes, the other thing in there is I'm calculating time, so I'm calculating the movement speed. So I'm making sure that things are going to just halt enough for the servos to move at a reasonable speed without trying to accelerate the servos so fast that the thing jumps off the desk, which can happen. I've got the detecting bounding box code in here, but I'm not actually going to use it. I'm going to do it separately because I don't really need to display this on the screen now. And in fact, my end target is putting this on a Raspberry Pi where I won't be able to do that. So we're again doing the same capture process we did previously. And here we go. We're going to go through this capture process. So we're going to capture. We're going to do evaluation. We're going to see also if we're going to do a bit of waiting around as well to make sure that servos have moved. So if it's time to do another check, or alternatively we have faces, then we will go into the process of finding out where that face is, the first one only, and then we will actually calculate where that face's mid position is in the frame, and therefore how far do we need to move the angle of the frame in order to actually correct it and move the face into the center of the frame. And that's basically what I'm doing. And so every time I'm going to go back into that do trans function to giving it a new angle for Z and Y in order to just correct where my position of my face is on the frame. And there are a few tolerances in here so that we don't keep moving around all the time. If things are actually reasonably centrally, we will leave it. And that's all that's in here really. Actually, it's reasonably easy to write and do, and it ends up with a reasonably good effect. Now you could get better on that, and there are things we could improve on, and I'll come back to them. I still have some bit more work to do with this project, not least working around the install strategy, so I can get this onto a Raspberry Pi 3A. Perhaps adding pig control would make the motion a bit smoother too. How would you move this project forward if it was yours? Let me know in the comments. If this video helps you out or sparks ideas for your own projects, consider supporting me with the super thanks button below the video, or there's a payment link in the description. I'm saving these up to get myself to the Open Source Conference in San Francisco 2026, and every contribution brings me one step closer, and I'd love to meet you all there too. Thanks again for watching. If you enjoyed the video, then please do give it a thumbs up and make sure to subscribe so you don't miss what's next. Why not check out my other projects too? I've got lots more on this robot xArm. Catch you on the next video. Bye bye for now.